So welcome back to this next session of this YM course, which intends to bring together both pedagogy as well as material science education content together in a manner that is relevant for materials educators today. So a quick recap to begin with. As we saw in the last class, we discussed the idea of constructing information, constructing knowledge. Knowledge maps were a good example of that. And the reason why this was a very interesting approach was primarily because of the fact that the human mind tends to construct information in a very specific manner, and it's helpful for us to actually understand that, because that enables us to in turn construct a lesson plan, in turn provide a framework by which we can provide content to our students in a manner that is sufficiently scaffolded and in a manner such that learning is enabled in a high efficiency manner. So in that context, we talked about constructivism, constructionism, connectivism. A good example of connectivism is in fact what is happening here between you and me, those of you who are observing, and me, because we are able to use technologies in order to create knowledge networks and connects, which previously was not possible. And the ideal situation would be to use these interconnects in order to facilitate learning. Design focused evaluation, and we did discuss about the various evaluation schemes that various teachers could use for their programs, for their courses. For instance, we could have the following. I'll just run you through this very quickly. Design focused evaluation was something that we discussed. These were the three assessment models that we discussed in the last class. Very important for those of us who have to do some form of grading. The most universally and globally accepted form is norm referenced one, wherein you fit students on a curve. There are statistical questions you could ask, which basically means that this approach would rather fail, in fact, and it would be illogical to use it if it is a very large, unless it's a very large class and a very heterogeneous class. Most of our classrooms tend not to be heterogeneous, so you have to think many times over before you do norm referencing. The other one is criterion referencing, wherein you say that this is sort of the criteria for assessment as far as I am concerned. This is the level of performance that I expect of my student, and use that rather objectively in order to evaluate the students. And the last one is ipsative, which is something that I am particularly fond of, wherein you say that the student was here when we started talking to one another, discussing with one another, and the student is growing when compared to where she or he was earlier. But really, you might have to mix these kinds of assessments on a need basis in a professional setting. For instance, most companies in their training programs use criterion reference. It makes a lot of sense. They don't use norm referenced. In university setting, typically it is norm referenced, especially if the classrooms are pretty large. I personally prefer mixing them up based on the situation that we have in hand. For instance, if there is a class wherein there is a lot of remedial teaching that is required, an ipsative approach might be very helpful for the student because it provides formative assessment. It tells the student that there is scope for growth and there is a certain progress that she or he has made, which is certainly a kind of positive reinforcement oriented statement that you are making. Over and above that, in the last class, we discussed this idea of schema, and this is very important because it actually tells you about the way in which we pattern information. So there is an information pattern, an information map in our mind. All our students come with their own schemas to the classes that we conduct. And the question is, how do you actually enable them to map out the new information that is provided to them into the schemas that they have in their mind? They have learned something. How do you actually enable this? Props can be very helpful, but also knowing your students and asking questions in a manner such that it is scaffolded is rather relevant in this particular context as well. So we did discuss schema, and we also discussed situated cognition, which is the emphasis on doing for learning. So for instance, this is particularly relevant for engineering education, because in engineering, doing is rather inseparable from knowing. For instance, if we talk about casting of a certain kind, if a person is doing the casting, he or she learns the casting process as well in the process. So the separation between doing and learning sort of being done away with is an idea that comes from this theory of situated cognition, and I think that there is a lot of value associated with it as well. So with that as the backdrop, we will quickly look into one more interesting idea as far as education research is concerned, and we will proceed. And before we move forward, this is something that I wanted to show to you in the last class, the Goodhart's law. When a measure becomes a target, it ceases to be a good measure. It's a very powerful and insightful law. It is not a law like a physical law, let us say the law of thermodynamics, but it is rather a law on human behavior, and it has implications to the way in which we conduct our classes. For instance, if our only intention is to ensure that our students get 100%, for instance, that becomes a target. So the score which is a measure becomes a target, and when that becomes the only target, teaching ceases. I mean, the real process oriented approach to classroom education ceases, and that can result in perverse incentivizing or teaching to the exam, which is certainly not good for the students' future, certainly not good for their formation. So I would encourage a deviation from the standard practice of teaching to exam to, let us say, teaching for formation, which is a fundamental different paradigm, I believe. So with that, let me just go to another interesting idea, which is again helpful in sort of developing lesson plans, and that's called the Piaget's theory of cognitive development. Let me just project it. I got it from a source, and I have also referenced the source. It comes from this source called Psychology Notes, and I'll just zoom it out. I hope the camera is capturing it. Yeah, you are able to capture it? Yeah. So typically the students that we are dealing with are adults, so they certainly belong to this category, and you will find that in this category students are capable of theoretical, hypothetical, counterfactual thinking. By that what we mean is you can actually get them to think in abstract terms, in terms of operating on information. You can also expect them to work with abstract logic and reasoning, alright, asking questions that are to do with assumptions, what assumptions are reasonable, what the structure of information is, and so on. And strategy and planning becomes important. You can also make them a co-partner in sort of or a partner in learning, primarily because they are capable of self-determination, and concepts learned in one context can be applied to another context. Today I'll try to do that. For instance, we'll talk about polymers, and some of these students would have learned some of those concepts in another context altogether, and we'll see which fraction of those concepts can be mapped to understand polymer science and engineering. Polymers being the special class of materials in this particular class that we will be discussing. So note that there is a mapping between this, very, very basic levels of learning that, let's say, very young kids do, and let us say the kind of learning that adults can do. There is a fundamental difference, and this maps out to the Bloom's taxonomy. If you look at Bloom's taxonomy, the very basic level is at the level of memory, at the level of understanding, at the level of just figurative learning. But it is not at the level of operating between concepts. It's not at the level of applying concepts. Okay, and finally, when you are applying concepts, you are creating a new idea, let us say, or you are analyzing a new idea, which is on top of the Bloom's pyramid, and you can see that it more or less is mapped out to this. So there is a very interesting challenge that educators face as a consequence. Now, when you give a first level exposure to students, they become aware at the figurative level. For instance, they must have heard the laws of thermodynamics from the time they were 15 years old or 16 years old. So they are familiar with the concepts, but they may not be able to transform the concepts. They may not be able to apply the concepts in a new context, and so on and so on. But students may not necessarily realize that. They may not necessarily have that internal reference that helps them realize that just knowing the law of thermodynamics or the statements of thermodynamics doesn't equal to knowing them at this level, at the formal operative level, at the level which requires you to apply, reapply, apply to a new context creatively, analytically, and so on and so on. So it is, as a consequence, I think, very interesting to think about how Piaget's theory of cognitive development maps or gives us insights into Bloom's taxonomy as well. And there's a rather interesting map that exists, a coherence that exists between the two ideas. And this is something that I wanted to sort of bring to fore in today's class. To summarize, in Bloom's taxonomy, there is a structure, there is a hierarchy of education, of learning that we are actually emphasizing. And it comes in the following manner. Let me just show this to you. So this is Bloom's taxonomy. So at the very basic level, you remember, in fact, very young kids also remember, small kids, sometimes as little as 2 years old, they do remember words. They may not fully understand the import of it, but they do remember. And slowly they are able to apply words, they are able to create their own sentences, structures, etc. And they might be able to create an entire story which is at the top of this particular pyramid. Likewise, students of science and engineering may be able to remember certain terms, for instance, entropy or laws of thermodynamics or continuity or limits, or differentiation or whatever, and they might be able to apply it in some context and finally apply it to a very new context and create a new idea. It becomes possible. But that basically requires them to walk up the Bloom's taxonomy. At some level, this has parallel with the theory of cognitive development, which is what I wanted to bring to the table, where when it comes to, let us say, language development, we understand that this is how human beings operate. They start to begin with purely motor response, touching, feeling, listening, and so on, then slowly start realizing that objects exist, shapes exist, and so on, and then they are able to sort of work with language in a very specific manner, may not be in a very novel manner, and finally they are able to use logic, reason in a very novel manner. So it is like walking up the Bloom's taxonomy in some sense. Okay, so there are very interesting parallels. Now let us see how this informs, let us say, education in polymer science and engineering. So we will take an example. Alright, so at a very fundamental definition level, we can ask a question like, what does a polymer mean? So it is at the figurative sense, at the most fundamental sense. Okay, what does a polymer mean? And I can come up with a definition and I can come up with a set of examples. Now let me juxtapose Bloom's taxonomy on polymers and concepts in polymers, and let us see whether that can enable us to ask questions, in turn find response to questions and learn the topic. Okay, that is an interesting way of thinking about this, isn't it? So I am going to show you the Bloom's taxonomy as a consequence. So why don't you discuss with one another? So this is the Bloom's taxonomy. Alright. So what do you think are some of the things we could remember about polymer science? For instance, the definition of various things. Okay, the definitions. I'll give you a set of terms. They may look disconnected, but let us just attempt to remember those. Okay, and when we look into the definitions, we'll slowly start understanding them. We look at some curves and see if we can apply those concepts. In some cases, we might show some curves and try to actually develop new concepts. So we'll try to operate here, at least to begin with, and slowly we'll try to move up the Bloom's taxonomy. So the first word in this particular class that we might want to remember is the word polymer itself. Okay, so let me write that down. So let me write down some words. Polymer, monomer, okay, molecular weight, number averaged molecular weight, and weight averaged molecular weight. So I am giving you 5 words, and what we will do is we will just remember them. So spend a minute trying to remember it, and then you can use the data that you have to find out the definitions of these. So there are 5 words there, and we are going to just remember them and see if we can understand them as well. So polymer, monomer, molecular weight, number averaged molecular weight, and weight averaged molecular weight. So can you write down these words so that you at least remember these words? Because writing is can be an active process. It can be a process that enables you to remember, recall facts, basic concepts, duplicate, list, memorize, etc. And in case you do not have data, I am going to project some stuff here that might be relevant for you as well. Okay, so I have written words. So these are words to just remember. And let us also say understand. We will look at the definitions of them. So remember the words and let us write down the definitions. Let us also understand them a little bit. So polymer. So this is one definition I found, okay, from a certain source. This is a definition that I have put for you. You might find alternate and equivalent definitions. Do you want to actually find one? So let us see if there are 2 or more ways of expressing them. Yeah, okay. So you have an IUPAC definition. Yes, please tell me.
A molecule of high relative molecular mass
This is interesting, no? So, because molecular weight or mass, alright. So, I will just put it as dash mass. So, this and this are connected. So, it has high molecular weight or mass, okay. So, there are repetition of a certain unit, okay. So, conceptually of molecules having low relative mass. So, these molecules having low relative mass are the repeat units. Is that the claim? So, clearly polymers are made up of multiple small molecular weight units. They are called monomers. Now, if they have to connect with one another, can you just take two random molecules and connect with one another, or would there be rules for connecting them with one another? There has to be some form of bonding. So, I cannot simply take two molecules and make them into a polymer, clearly, you know. So, but for the sake of a prima facie first level definition, it suffices to say that polymer has large molecular weight. It is made up of repeat units that have small molecular weight. Interesting. So, these three words are actually connected to one another, right. Can we take some examples of monomers and corresponding polymers? Can we take a ethylene is a monomer. So, ethylene is a monomer, okay, and if I polymerize it, I will get polyethylene. I am just going to write it as PE for the time being, okay. Now, can you polymerize it indefinitely? Will the supply of ethylene molecules be infinite, or would it be limited by some reaction conditions and so on and so on? It would mass, right. So, if I am going to start with, let us say 100 molecules of polyethylene, let us say that 99 of them may have the probability of coming together to polymerize. So, there is always a probability of reaction. There is a probability of reaction, and what does not react actually stays back, but clearly it is limited by the initial mass that you take and the reactivity of the molecules concerned. So, in fact, that limit is actually called the Carothers limit, okay. So, I can say that the possible probability of reaction, for instance, is 0.01. So, if I have 100 such molecules, then the number of molecules that are undergoing reaction would be number of molecules that is the 1 minus the probability multiplied by the number of initial molecules, correct. So, if I start with 100 molecules, 99 of them are reacting, 99 of them would be reacting. So, that means that single molecule is in equilibrium with this polymer. There is another way of thinking about it. So, there is a thermodynamic way of thinking about this. Alright. So, this being a probability, it is a bulk probability, it is a term. If I have 100 molecules, 99 of them will react. If I have 200, 99 into 2 will react. So, those are actually average numbers. So, these equations are relevant in bulk limit, in thermodynamic limit. Okay. So, let us look at the definition of number average molecular mass or molecular weight and weight average molecular weight or weight average molecular mass. So, let us look at that. Do you have some equations corresponding to them? If so, can some of you go and write it out there? So, you can erase this part and we can write it. So, you might see some numbers, no? Some equations might be there. Yeah. So, you have seen some equation there. You are also seeing some equation there. Do you understand what that is? So, the first step is we can actually even memorize the equation. It makes sense. And then we can start seeing meaning in the equation. That is also fine. Okay. So,
this is written from memory.
Okay, fine. Yes, very good. So, Bodhi, do you want to erase that part and write out the two equations you know? So, as and when he is erasing, let us just revisit and first of all familiarize ourselves. So, polymer is a word, monomer is another word that we looked at. Then we looked at the word number average molecular weight and mass averaged molecular weight. We have not looked at the definition yet, okay, but polymer and monomer we made some sense of it, alright. So, polymer is a substance which has a molecular structure built up chiefly or completely from a large number of similar units. What are these similar units? Monomers. Bonded together. Can you take just any two random monomers, or can you take just a monomer, any random thing that doesn't react, for instance? It's just not possible. They have to come together in order to form bonding, and typically polymers have a fair degree of covalent backbone. Okay. Example, many synthetic organic materials used in plastics and resins. Okay. So this is the equation for number averaged molecular mass. Can you also write down the equation for weight averaged? So yeah, you can just use the information that is available. You just replace that Ni with Wi. That will solve the problem. Okay. So please write it down. So Malik, do you want to go and help? Go to the board. Yeah, that is correct. Wi, Mi. Yeah. Very good. Let me make a parallel with something that you have seen perhaps in your basic statistics. So you have written, let us say, if you have xi, which is a set of random numbers, summation xi divided by n, where n is the total number of x, is basically the average. So it is summed over all of I. Here you are basically saying that I am not just going to sum over, it's a weighted average. What do I mean by weighted average? Suppose this xi appears fi number of times. Okay, then the average here will be summation fi xi divided by summation fi. Correct? And that's called the weighted average, and that is what this is. So this looks more like a weighted average expression as opposed to just the usual average expression that you have seen. What are the weights that you are using? You have identified I units in your polymer. So you take the polymer, you have identified this unit, then some other unit, you label it, okay, you have identified units, and you have the mass corresponding to them, and this particular unit is repeating ni number of times. So I identify, let us say, 3 different parts to the polymer. I know the mass associated with 3 different parts of the polymer, and I know that the frequency with which each of those 3 parts occur are n1, n2, n3. So I do summation ni, mi, that means n1, where n1 is actually the number of times that particular unit repeats, okay, that particular unit is present in a polymer, multiplied by the mass of that, divided by summation ni, which is the total number of units that is there in the polymer. Similarly, in this particular case, I do not necessarily just do ni, mi, I am basically going I am doing wi, mi. So wherein I am saying that this particular polymer, it has 3 units. The weight of this is so much. The cumulative weight of it is what I am actually doing when I am actually doing summation wi, mi. You know, so wi. So remember, there is a big distinction between this and this, as he pointed out, is if I just multiply this by the mass of I essentially get wi. So what I am doing here as a consequence is I am saying I have ith unit, this is the mass of the ith unit, and this is the total weight associated with the ith unit, okay, and that is what I am actually putting here and dividing by the sum. So let us take a look at an example, alright. So once again, to recall, this is called as the number averaged molecular weight, and this is called the weight average molecular weight. Why is it called weight average? Because the weight of the ith unit is the weight. So it is a weighted average as written here, and here it is number average because number is the weight that is used here. You understand? So now let us take a look at an example, for instance, and this comes straight off teaching source. So here is some data that has been collected about number of molecules and mass of molecules. So I am saying that I have different kinds of molecules within the polymer, okay. So in a polymer chain, I have 1 unit that has this mass. I have 3 units that has this mass, okay. I have 5 units that has this mass, and so on and so on. So I know the number of units. So this is, let us say, I is equals to 1, 2, 3, 4, 5, 6 and so on and so on. This is Ni, Ni is 1, 3, 5, 8, 10 and so on, so on. And this is the mass, this is Mi. So I just plug the equation, and with this can I also find out the weight average molecular mass? Obviously. So from this you can find out both the weight averaged molecular mass as well as the number averaged molecular mass. Okay. So do you want to just, you don't have to solve the problem, but can you just write out the formula, apply the formula in the context of this, and just so that I know whether you have understood or not. So the mass exists, the number exists. Are you all able to see the data? So you can map it out to this formula, for instance. So you can put I here, I can be 1, 2, 3, 4, 5. This can be N1, N2, N3, N4, N5, N6, N7, N8, N9, 10, 11, 12, 13. And then this one will be M1, M2, M3, M4 and so on. So you know what your I is running from. I is running from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So you can show your workings to one another if you want. You understand the question? Also, do you think that this and this would be the same or different? Very definitely different. The weights that you are using are very different. So can I look at your working, please? So can you just substitute? Just substitute. You have written it correctly. So just show me how you would do this. Yeah, in the lab, for instance, if you had this kind of data, you could just do Excel, right? Could just do Excel, or you could use Origin or whatever. Yeah. So you have written I is equals to 1. So 1 into 8, 8 into 10 to the power of 5, correct. So this one is summation Ni Wi divided by summation Ni. That's what you want to do here. So divide by summation Ni. That is good, correct. So you understand at least summation Mi Ni divided by summation Ni. What about you? You also understand that. Can you also write down MW bar? Just below that. You don't have to work it out. Just write out. Just apply the formula. Are you able to apply the formula? Yeah. No, just forget it. I'm just asking you to look at this formula and apply it. So this is Ni. I is running from 1 to whatever. This is Ni and these are the weights. I'm just asking you to apply the formula. Mn bar. You don't even have to solve the problem. Just apply the formula, show the working. First step. That's all. Nothing else. So here you can see the way it has been done. Number of molecules. It's exactly this. Okay. So I is going from 1, 2, 3, 4, whatever. Ni is 1, 3, 5, 8 and so on and so on. The mass of the corresponding molecules, the ith molecule is given, and then they are basically calculating Ni into Mi. So they tabulate it, you take the sum here, divided by the summation of Ni. That would give rise to this number. So that is summation Mi Ni, you divide it by summation Ni and you would get a number. And similarly, yeah, you can get weight average molecular mass. For weight average molecular mass, they have actually Ni is there, Mi is there. So you have calculate Ni Mi. Okay, that is not sufficient. You have to multiply it by the mass again. Okay, and then you calculate summation Wm, Wi Mi divided by summation Wi. So it is actually a weighted average, right? So this value, there is the number average molecular weight and weight average molecular weight. What you will notice are just they are just weighted averages associated with the molecular mass of a polymer. So what are the words that we learned? What are some of the things that you learned? Polymer, monomer, and monomer is a repeat unit, molecular weight, number average molecular weight, weight average molecular weight. Now we will ask some questions. Okay. Now suppose I want to study the strength of a polymer. Alright. Which do you think would be more telling, important? Would it be the number averaged or the weight averaged molecular mass that is likely to correlate with the strength of a polymer? When I know the composition of the polymer, of course, number one. Okay. Keeping all other quantities constant, that is materials processing related aspects constant. Number two, I want to look at how this polymer will flow, its viscosity. Okay. Which of these two Which of these two would have a more telling impact on viscosity? So why don't you write down this question? Another way of asking this question is, I have remembered something, I have understood something, how can I apply this? So what are the physical, chemical or engineering applications for which I can use the number averaged molecular weight or the weight averaged molecular weight? You understood? So discuss with one another for about 3 minutes, and then you can use, and then let us say use a prop or so, alright. So can you discuss with one another? So think about it. So the distinction is the weight that you are using. Now based on the weight that you are using, what do you know about the polymer? What characteristic or feature of the polymer are you getting to know? That's the question. Okay. So can you discuss with one another, please? Do you understand the question? Yeah. So I have written down 2 types of equations. What kind of properties will correlate better with this equation? What kind of properties will correlate with the other kind of equation? That's another way of thinking about it. You understand the question? You understand the question? So write out or guess a set of properties that you think will have better correlation with, let's say, number average molecular weight. Okay, and guess a number of physical properties. It doesn't matter if you are wrong or right or whatever. You just guess and give us a physical reason. It could be an intuitive reason. It doesn't matter. That's part of the schema that you come to the class with. So it could be an intuitive reason. So what is it that you think would be a set of properties that correlates with MW bar, and what would correlate with MN bar? You might not have a fully formed reason even. That is also fine. But just to communicate, articulate. So discuss with one another. Now, some of you might be more fond of chemistry, some of you might be more fond of physics, it doesn't matter. But what do you think would be the kind of physical properties or chemical properties that could correlate with this? Or physico-chemical properties or thermophysical properties that could correlate with each of these things, okay? Are you making some progress? It's okay if you are not making progress also, you can just tell me, as long as you are putting up a fight, it's perfect.
Actually, we are thinking weight average will plays a role in this viscosity, and this number will plays in strength.
Why? Yeah, you are right. Why do you think it is right? It's about right. These are all approximately reasonable statements. Yes. Tell me why.
Like if it is a very high molecular weight, the viscosity will be very less because all molecules are. So maybe we are increasing the temperature.
So viscosity depends on the transport property, right? So if it is on an average having higher weight averaged molecular mass, then the viscosity is expected to be higher, isn't it? And
this number average molecular weight plays a role in strength. So the weight here doesn't come into factor. Like some molecules have less weight, they have very high strength.
So strength and weight could be completely decoupled for all. For instance, you could have very high strength to weight ratio for, so you could keep the weight constant and you could improve the strength by basically playing with your NIs. That's another way of thinking about it. So that's a very good thing. So why don't you now look for some information about some properties that correlate with summation MI divided by summation NI.
I think mostly mechanical properties related to that will come under
right.
number average and something like
anything that is yes, a lot of transport related properties would depend on summation MI WI MI divided by summation WI. Okay. In fact, even things like specific heat capacity would have a very strong correlation with summation MI WI divided by summation WI. Makes sense because it depends upon the degrees of freedom and the total weight of the system. And yes, what are your arguments?
We are thinking that this, for example, in cases like molecular weight increases means melting point and molecular weight is problem.
Okay, why would that be the case? But why would van der Waals force depend on the weight? Van der Waals force depends upon whether there are polarizable systems. If there is sufficient polarizability, if you have one very polarizable object, another very polarizable object, there can be secondary forces between the two, which is the van der Waals interaction or the London interval.
Molecular weight means more number of bonds also there.
Need not be, it could be just a very heavy set of atoms. No?
Actually, I was also thinking that bonding is mainly the interaction of electrons. So whether it really depends on the atomic mass.
Hmm.
But
No, it's not.
again,
It
if
will
we
depend on molecule. I mean, for a molecule, I think it increases.
okay, molecular weight is the sum of atomic masses. So, but I think atomic mass will still affect somehow because if
Yeah,
you
yeah.
are having a very
Absolutely no question. I mean, there is no zero correlation that we are talking about between any property and MW bar or MN bar. There cannot be zero correlation. But the question is, which one is likely to give you a better correlation? Let's say, as they were saying, if you look at strength, for instance,
I think that
is
strength will be given by number average.
yeah, that is right. So it is MN bar. Why do you think so? Intuitively, you can give an explanation.
Because strength depends on the depends on how long the chain is. Longer is the
Long,
chain.
and also things like how easy it is for you to deform the chain, for instance, right? And why would that depend only on the number average, not on the weight average? How do we define a mechanical property? For instance, Young's modulus, delta L by L. Where is weight there? Yeah, so there is no weight there. You are looking at the change in deformation, right? And it could be a heavy object which is stronger, a light object that is not very strong. It's possible, or vice versa. A light object that is very strong, aluminum, for instance. Yeah. So clearly, you are absolutely right that strength has a better correlation with MN bar. On the other hand, transport properties, anything that is transport related, diffusion, viscosity, and so on would actually depend upon, and certainly vibrational properties would depend upon, yes. So why vibrational properties? Because vibrational properties depend upon the atomic masses also, correct? Naturally.
Viscosity will depend on the
Viscosity will depend, diffusion coefficients. So if I take this polymer and I look at how it diffuses across a solvent, then the diffusion coefficient will definitely depend very strongly on the MW bar, right? The viscosity would, no question about it, right? Its spectroscopy, let us say infrared spectroscopy or Raman spectroscopy will definitely depend upon the MW bar also, correct? But on the other hand, the mechanical properties by and large would actually depend upon MN bar. So there is absolutely no situation wherein you have zero correlation between one and another. That's not what we are asking. Where do you expect stronger correlations? That's another way of actually thinking about it. You understand this? So what is boiling point in the context of polymers? So it's very nice that you bring that up. So that is in the context of physical properties, maybe even arguably physico-chemical properties. So you talk about boiling point. Let's also talk about melting point and something called glass transition temperature. Let's talk about three different things. So one is boiling point, melting point, and glass transition temperature. Okay. Now, if I have a liquid and I heat it up, okay, it vaporizes. The point at which the vapor pressure is in equilibrium with the liquid is called the boiling point. You know that. That is the thermodynamic definition of boiling point, right? Similarly, I can start with a solid, it can get into an equilibrium with liquid, that point would be the melting point. So this could be defined for a polymer, because polymer can be solid, I can heat it up and it might actually become a liquid, and the point at which, the temperature at which it is in equilibrium with one another can be defined as the melting point. What about this glass transition temperature? Can you use your systems and tell me what this glass transition temperature is? And we'll also think about why I should bring this concept of glass transition temperature when we talk about polymers. Let us look at the formal definition. So this is at the level of remembering. So first of all, remember the word glass transition temperature, remember, and then let us understand. So let's at least define it in some way, and then we'll start applying it, alright. So that makes sense, right? So we build on top of very basic premise and knowledge that is available.
The temperature at which polymer experiences the transition from rubbery to rigid state.
So here, this is interesting because they don't call it solid and liquid. What do they call it? Rubbery and rigid. Okay. So you have the rigid state, which by and large is transitioning to a rubbery state. And notice that I am not using a double arrow. Okay. It doesn't matter. As I increase the temperature, it goes from rigid to rubbery. As I lower the temperature, so this is actually, let us say, increasing the temperature, and this is decreasing temperature. So we have to ask some very deep questions now about this, right? So first of all, what is the definition that you said? It is the temperature.
The polymer experience the transition from rubber to this.
So what does rubbery mean?
Polymer.
Means it's a little deformable, right? It is flowing a little bit.
I mean crystalline to amorphous.
So is it limited to polymers, this definition?
Of course not. Because you have not seen it as part of the definition. Of course not. But it need not be. Glass transition can happen for glasses, silicate glasses for instance. I can heat, which are ceramics. So this glass transition as a consequence, though we are learning it in the context of polymers, can be easily extensible to ceramic glasses, and in fact also things called metallic glasses. This is a rather new class of materials. This one is very new. This one has been around for a long time. Human civilization has been using ceramic glasses for a long time. Okay, polymers have become increasingly common in the last century and this century, but have not been so extensively used. Natural polymers, of course, have been around for a long time. Textiles, for instance, have been around for a long time. But ceramic glasses have been around for a really long time. Metallic glasses are a very recent phenomena. Okay, now that is interesting. Okay, so glass transient temperature, we are learning it in the context of polymers, but there is nothing that is specifically polymeric about it. It's a concept, and let us try to delve into the details of this concept. Can you use your data and tell me the glass transient temperature of some polymer, and let us see how it is defined, how it is given, the data is given. So please.
Polyethylene.
So there is some data, and of course it's not any polyethylene. Remember that there are many different kinds of polyethylene, because it's low density polyethylene. Again, you will have to define something called the number average molecular mass or the weight average molecular mass, and so on and so on. These are important. Okay. For this one, minus 110 degrees Celsius is what? The glass transition temperature. Do they qualify it at all? They are not qualifying it. Now I will show you one additional data over and above that, and you tell me whether what they have done there makes sense or not. So this is the polymer in glassy form, highly disordered form. It's pretty amorphous, but it undergoes this glass transition, and this glass transition is actually a very nonlinear change in the specific volume as a function of temperature. Remember that if I take an object, let us say a metal, I heat it up, the tendency is that it will expand. Okay. So specific volume is nothing but the volume per unit mass. That is what, or volume per unit mole. That is what is plotted here. And as expected, over a certain temperature regime, it's linearly increasing. That means this polymer is indeed expanding. But look at this. At a certain temperature, it is no longer linearly expanding. It should have expanded like this, but what has happened? It has just taken off. So it's become rubber-like, it started flowing out, you start seeing molecules slide past one another. Typically, and this is a thumb rule, the temperature at which in your system, about 50 molecules sort of slide past one another. Okay, so you have an ensemble, you have a neighborhood of molecules. If they are able to start jiggling past one another, that would be roughly the temperature that corresponds to this. Now this is interesting, isn't it? Because now I can ask a question. I have two glasses of the same composition. Am I guaranteed to have the same glass transition temperature? I have two glasses, I have two polymers having exactly the same composition. Am I guaranteed to have the same glass transition temperature? Please discuss this question with one another. You understand the question? Your discussions are valuable. Please discuss. And it doesn't matter. You could be right, wrong, anything, but just put up a fight. So what is your answer? I have the same composition, 2 polymers, same composition. Am I guaranteed to have the same TG value? Why?
Because these are amorphous systems.
Amorphous systems, and they depend upon the packing arrangement. So I could let us say make this polymer, slow cool it and make it very, very ordered. I could make this polymer, same composition, make it disordered. With minor variations in order, I could have very drastic changes in the glass transition. So that is interesting. So the glass transition temperature doesn't depend on the composition alone. It depends upon the process that you use for making the polymer. It depends upon the process that you use for making the glass. It depends upon the process that you use for making even the metallic glass. So this is interesting, isn't it? So we are developing a concept and we are going even beyond polymers for that, because it's a sufficiently general concept. Now let us spend some 3 minutes interpreting this graph. So you have some graph there, okay, that is your data, and let us spend a few minutes interpreting this. So for instance, this is there, you have a graph C, you have a graph D. This TG stands for glass transition temperature, TM stands for melting point. So clearly there is a distinction between melting point and glass transition temperature, right? And then you have one set of curves, you have another set of curves. Notice that here there is a discontinuity as far as the curve is concerned. Here there is no discontinuity at all, it is continuous, correct? So if you had to look at it mathematically as a curve, describing the curve, I have a discontinuity, I have a step function here. The derivative here is different from the derivative here, in fact derivative is ill-defined here. Here on the other hand, I actually have the derivative that is defined, very well defined throughout. However, at this particular point there is a deviation from linearity. At this point as I come down again there is a deviation from linearity. Rather interestingly, this when extrapolated gives you something called the glass transition temperature. Note that it is an arbitrary definition. There is no one temperature at which TG happens. For instance, instead of this definition, I could have actually used some other extrapolation, isn't it?
So can it lie on the right side of TM?
Can it lie on the right side of TM? Is it allowed or disallowed? Of course not. Because on the right side of TM, you are only allowed to have, okay. By the way, this is an interesting question. Is there a lower limit to TG? So his question is, you know, can I have this here? The answer is no. So another question is, can it be here? Can it be here? Can it be here? Can it be here? What is the limit? That's his question.
0.5 TM.
Huh? Why? How do you know? What is the guarantee of that 0.5 TM? So you understood his question. His question is, what determines this gap? Can I make it infinitesimally small? Can I make this gap such that it is no longer lying here, it's lying here. It's not lying here, that we ruled out as a possibility. But what is the limit? How close can I bring it is another way of thinking about it, right? It's another way of thinking about it. Very good. So I'll leave this as a homework for you to think about and we'll reconvene. So with that we come to the end of this session. So to summarize, so we discussed essentials of pedagogy. In the last class, the various pedagogic terms that we encountered was recapitulated, primarily constructivism, connectivism, and then learning in the context of constructive alignment, and we also looked at evaluation theories, and today we looked at the Piaget's cognitive development and how it rather nicely maps on to Bloom's taxonomy. And we also use Bloom's taxonomy to create a lesson plan in the context of polymer science and engineering. So by the way, Piaget's theory is about cognitive development, about how human beings learn. It's primarily about how children become adults and how their learning styles vary and change, how their ability to do abstract thinking increases, and we usually deal with students who are capable of abstract thinking, but still you may want to get them started at the lower levels of the Bloom's taxonomy and then finally get them right on top of the Bloom's taxonomy. That is more or less what we are doing right now at this particular point when I said that is homework for you, because number one, a concept that they had encountered in the context of polymers, we try to generalize it. So that is applying it looking at it as a sufficiently large operator that is operable over a larger space than is usually mentioned in a textbook, so that they get to think about constructive, creative ways of constructing their own knowledge. Alright. In the context of polymer science, we looked at some terms. We started with rather basic ideas like polymers, monomers, which are the repeat units. We looked at the definition of the same, the formal definition. One of the students in fact read out the IUPAC definition of the same. Then we looked at the distinction between weight average molecular weight and number average molecular weight, and the students were able to deduce by themselves the kind of physical properties that might be strongly correlated with, let us say, number average molecular mass. They were independently able to rationalize through intuition perhaps, but rationalize nonetheless, and that is what is very important for us to take home as teachers, that students are capable of intuiting, and that is essentially an evidence that they bring their own schemas to the table in the classroom setting. So they identified that strength, for instance, can be expected to have a fair degree of correlation with number average molecular mass, while transport properties in particular, and certainly even vibrational spectroscopy would have correlations with this. Not that there will be zero correlation with this, but in terms of sort of stronger correlations, those are what we would actually expect. Over and above that, in another context, a student directly came up with the idea of these three temperatures, and we looked at the formal definition of this temperature, and then we started asking what is unique about it, and we realized that two polymeric systems having same composition need not have the same glass transition temperature, because it has to do with the intrinsic order that is corresponding to that polymeric system as well, which is a function of the processing. And given that you can have the same composition differently processed and as a consequence very different glass transition temperatures. So we looked at a graph like this, and the student asked a very interesting question: can you sort of flip this, for instance? Can you have a situation wherein this goes here, alright? And we immediately ruled that out as a possibility, but then I asked them another question: okay, what determines the limit of how big this window is likely to be? Can it be infinitesimally small? Can it be infinitesimally large? If so, what determines it, is the question that I wanted them to think about. So with that question, we will stop here. So we will reconvene here for the next SWAYAM session. Thank you very much.